So as the brief introductions here, the group that I got together for this call are my co-authors on a recent paper that we had accepted at the CCS conference on end-to-end encryption for decentralized group communication apps. Could be messaging, could be collaboration, that sort of things. And of course, like for the technical details, you can go and read the paper, and that's available. So I thought what would be nice for this is to have just a bit of a discussion about the why, the background story, what got us interested in this, why the existing approaches don't do what we want, what kind of things we're hoping to achieve with this, and like just get a bit of the human background of it as well, like a bit more like what you would get at the hallway in a conference, maybe, rather than what you would get from the formal presentations. So yeah, kind of briefly introduce. So we have Matthew, who did his master's with us in Cambridge a few years ago and is now doing his PhD at CMU. We've got Daniel, who is a current PhD student in our group in Cambridge, and Alistair, who's the professor in our group and has been the senior person working on us with this stuff. So yeah, let's talk about encryption. So I think to frame the thing to start with, I'd say there are kind of three different ways in which encryption is commonly used nowadays, and it's maybe useful to distinguish them. Number one is encrypting a connection, like a TCP connection over the internet using TLS or SSL. And that's very well established, and we use that every day. That's fine. Then there's the kind of like application level encryption of PGP or tools like that, where you have the user very explicitly aware of the fact that they're encrypting something and then sending it as an email message or something like that. And then there's the modern messaging apps like Signal and WhatsApp and Telegram and a bunch of others, which also do encryption, but they do it end to end. So that means that the server can't see the plain text, which they could with the TLS connection. But on the other hand, it's kind of more hidden from the users. So I don't know, Alistair, maybe do you want to start? Do you want to say a few things about like those different types of encryption and how we're thinking about those?
Yeah, so I guess PGP has had a really bad reputation in the research community for being very difficult to use. There was a very famous paper called Johnny Can't Encrypt, and follow-ons like Johnny Still Can't Encrypt, which are definitely worth a look at. And so I think the shift that we've seen with end-to-end encryption in messaging apps is really exciting in the sense that it is much easier to use and provides good security for users. And the challenge, I guess, with this paper that we were thinking about is how could we potentially extend that use case to one where we've got groups of users who wish to collaborate on some data or data structure, and that for those devices potentially to be able to work either locally rather than over the internet, or to be able to work offline. And so that's sort of one of our kind of established motivating principles behind what we've been doing.
Exactly. And so like there's things like the key management, which things like Signal do automatically. So you don't have to worry about the fact that I have this public key, I have this private key. Which key do I give somebody so that they can contact me? All of that sort of complexity that you get with PGP type apps. But also, I think the security model has changed quite a bit. So like the modern messaging apps provide these concepts of forward secrecy and post-compromise security, which we've been thinking about a fair amount. Maybe Matthew, do you want to say something about those?
Sure. Yeah, so I guess you think of something like PGP, basically the assumption is that private keys stay private forever. You never have to worry about them getting leaked. Whereas with forward secrecy and post-compromise security, you're saying like, well, in practice, if you're using these keys for a long time, maybe they'll get compromised eventually. And we want to still provide good security guarantees, even given that the keys are going to get leaked. So yeah, I guess like formally forward secrecy is like saying, if you compromise my keys now, you can't read past messages. post-compromise is the other way, saying if you compromise my keys now, you can't read my messages indefinitely into the future. But basically, it's just like, yeah, in general, change your keys occasionally so that you're not always using the same keys.
It's quite amazing, actually. Like, you might think that if a key is compromised, all bets are off. There's nothing you can do. But actually, it seems like there are some useful properties we can still provide, even if there's a key compromise. Yes. Sorry. You go ahead, Alistair.
So, there are some caveats on that. So the assumption is that, of course, the device is compromised for a sort of period of time, and then after that, the security of the device is recovered in some way. So maybe that's through a software update, or the user reinstalls their device. And so that's the area in which post-compromise security then applies. And so if you looked in the sort of GPG case, once your private key is out, that's it. Even if you reinstall your operating system, once you put your private key back on there, you're still compromised. But this post-compromise security is really helpful in tackling those kinds of situations.
Yeah, exactly. So, so these properties of forward secrecy and post-compromise security are stuff that we want to provide. And you don't get that from like just having a public key, using a public key to encrypt a message to someone, because if that corresponding private key is ever leaked, then all of those messages can always be decrypted in the future. So we need to think about the protocols in a different way in order to achieve these properties. And I guess a starting point for that for many protocols is the signal protocol, which is a pairwise communication protocol, right? So it's just connects one user with one other user. Daniel, do you want to say a few things about that?
Yeah, sure. Signal protocol is basically the go-to choice nowadays for pairwise end-to-end encryption. It's what's used by Signal, obviously, by WhatsApp. And how it works is to have these forward secrecy mechanism. There are these ratchets that only go forward, and each side has a copy of the other side's ratchet. So when I receive a message from Matthew, I know his ratchet went ahead one turn, I turn mine one turn, and able to decrypt it. But from the state that I'm now in, I'm not able to go back because that ratchet, that cryptographic construction prevents me from doing so.
And the ratchet is typically implemented with a hash function, for example, isn't it? So like you can compute the hash function easily in one direction, but not in the other direction.
Yeah, exactly. And then when you periodically reset these like send and receive ratchets, with, for instance, something you do with Diffie-Hellman, then you get also your post-compromise security. So that's the basic building block. And I think that was quite a big success because that brought very, very strong cryptography to over 1 billion people on the planet and made it quite easily usable. And it works perfectly fine even with like the odd message get lost or reordered along the way, because you can at least buffer some of the ratchet states as you go along and then hopefully sort it out. And yeah, it's pretty fascinating that this works quite well and got adopted widely so quickly.
Exactly.
And another interesting thing about that is that it didn't come out of, like usually you say like with crypto, like, oh, don't do it yourself, let the professionals do it. I would say the inventors, they're not really professional cryptographers, but now like since then, professional cryptographers have spent 5 years like studying it and like working, taking that as the basis point.
And results have been quite good from those academic studies, haven't they?
Yeah, maybe. Haven't really found any serious issues with it.
Yeah, a few small things, but they're mostly questions of like how precisely do you formalize something like post-compromise security? Like exactly where do you draw the boundary between things that are secure after compromise and those things that are not secure? Yeah, so we have the signal protocol, which is great for one person communicating with one other person. One might naively think that, okay, it's straightforward to generalize from 2 people to 3 or 4 or 5 people, isn't it? But actually it turns out that it's not that straightforward at all. Do you want to comment on that, Matthew?
Sure. So let's see. Well, I guess the easiest thing you can do is just have separate two-party conversations with everyone. But this, you'll eventually run into trouble once you get to maybe a few dozen users. This just takes a lot of CPU time to have to do these, like basically with each message, you have to do a public key operation per person you're sending a message to. So if there's 100 people, that's 100 public key operations, which will actually take like several tens of milliseconds maybe just to send a message.
Also, the messages get quite big, I guess, if you have to individually send the message to every single person in the group.
Mm-hmm. Yeah, because then you can't broadcast your messages once. You have to send them once per every other user. Yeah, so I guess there's interest in, instead of trying to use these two-party protocols, you want to make shared keys, which are like symmetric keys that everyone agrees on, and then use those to encrypt messages. So you just encrypt them with one fast symmetric key operation and then broadcast it to everyone.
Mm-hmm.
So I guess, yeah, the easiest way to do this is with the sender keys protocol that's used by WhatsApp groups, which is where basically the first time you send a message, you choose a random symmetric key and you send it to everyone else and say, hey, I'm going to use this symmetric key from now on to encrypt my messages. And in the future, when you want to encrypt a message, you just use that symmetric key or maybe like a hash of it going forward. So that way you can just broadcast it.
Okay, so that sounds kind of nice and easy to understand. So if I want to send a message to all of you, I'm going to make up a fresh key. I'm going to send that key to each of you individually. And then thereafter, I can send my actual messages just unencrypted under that key. And that does mean now that if I ever want to change my key, then I have to send individually a fresh key to all of you again, don't I? Mm-hmm. So what does that mean then for the cost of achieving post-compromise security in this sender keys model?
So then actually, so if you're worried that like my device has just been compromised, maybe someone has seen all my keys, then they've not only seen my symmetric key that I use for sending, but also everyone else's symmetric keys that they used to send to me. So if we want to fix this, then everyone has to update their keys. And that's going to require basically like n squared new messages where n is the number of users, because each person has to send out n of these normal pairwise messages saying, here's my new symmetric key. And so that happens 10 times.
Okay, so that seems like we have, firstly, the signal protocol where every single message goes via the pairwise channels. We have sender keys, which is more efficient for each individual message, but instead the cost of doing a key update for after a key has been compromised is n squared. That's not great either. So then what else is there? There's the MLS protocol that is being developed by an IETF working group. Maybe Daniel want to comment on that?
Yeah, I'm not sure how much into the details I can go.
That's fine.
But yeah, basically the idea is you kind of, what Matthew described is, okay, everyone pairwise agrees on a key. What would be convenient is we have one key for the entire group. And to derive this key, we, like all the participants somehow have to agree on it. And the way NLI works on a very high level is that you have this tree structure of Diffie-Hellman operations, so that you can derive one group key from the input of all of the people involved, and that only takes logarithmic effort. But what it requires, at least in the version that we consider now, is that you have some kind of central server that gives you an ordering of the messages. Because if you don't have that ordering of the messages, different subgroups might arrive at different keys. And that is not very helpful when you then try to send messages. Maybe Matthew, you can add to that a bit more detail if I missed something important.
No, that sounds great to me.
Yeah, I think that's great. And so we get logarithmic cost because we've arranged all of the users into this binary tree structure. And so if a user wants to update something, they only have to update the path from their own place at the leaf of the tree. up to the root, and that the root of the tree is the shared key that is shared between all of the participants in the group. It's a very nice construction, but yes, it has this problem that it requires that all users see the same order of messages. And that's problematic if you want the system to be decentralized, isn't it? Alistair, do you want to talk a little bit about decentralization?
Sure. So if we want to be able to cope with mobile devices using this, and in particular, if we want to have mobile devices that perhaps they're connected to one another, but not connected to the wider internet, and we'd like to be able to allow that communication to happen, updates to flow, for example, messages being sent. Well, here we might think of messages rather than just messages inside a WhatsApp group. Maybe these are update messages around collaborating on a Google Doc or a calendar or a to-do list. And so we'd like local clients on local devices to be able to make progress and protect their communication with end-to-end encryption without requiring them all to be connected to a central server at all times.
Yeah, and this is like a principle that has been going throughout our other work as well on CRDTs, for example, where the essential idea is like if you have any two devices that are able to communicate via whatever communication channel might be, and this might be Bluetooth between two devices without going via the internet at all, then we still want those two devices to be able to communicate and collaborate and make progress in exactly the same way as they could if they're connected to the internet. So that we simply don't care what the network topology is or what the connectivity is right now. We can just use any communication channel that exists. And that's really liberating from the point of view of building applications. But it means that, if you have the phone and the laptop that can only communicate via Bluetooth, and there's a central server that is in charge of deciding on the total order of all of the messages, well, the messages via Bluetooth are obviously not going to go via the central server. And so therefore, they're not going to benefit from this ordering. And so this means we can't use the MLS protocol because it has baked in at a really fundamental level this assumption that everyone is going to update the keys in the same order. And so that simply won't work in a decentralized setting. You simply can't use the protocol. And so this leads us to the protocol that we designed and that we wrote about in the paper. So it's a protocol that is decentralized, so it allows any subset of users to communicate and make progress and even add and remove group members without necessarily being connected to any majority of the group or any servers or any other assumptions about connectivity. And at the same time, it still provides the post-compromise security and forward secrecy that we were talking about, and also it's reasonably efficient. In particular, it's less than the n-squared cost of sender keys. So maybe, Matthew, do you want to give a summary of how our protocol works?
Sure. Yeah, so instead of n-squared, we get these n-size updates. Basically, well, the basic idea is the same as sender keys, except when you send an update because you think you've been compromised, instead of telling everyone else to please update your key, you just send out one new secret value and you say hey, everyone, please use the secret value to update your current sending key. So then everyone will use some hashes of this random value and then hash that together with their current sending key, and that gives them a new sending key, which is protected against your prior compromise.
Yes, and then the key idea here is that not only you can update your own ratchet, your own sending key by sending a secret, but also then if I receive a secret from Matthew, say, then I will I will broadcast to the group an acknowledgement of this fact. And so how do we use those acknowledgements then?
Yeah, so let's see. So that's part of ensuring that people see the same, well, it's about ordering basically. So if I'm receiving a bunch of different updates from people and updating my keys, I might receive those in a different order than everyone else does. So acknowledgements tells everyone oh, actually I received this key and then that key and then that key. So if you want to be able to keep your copy of my key in sync, please do those updates in the same order, even though maybe you got the update messages in a different order originally.
So that's quite an interesting insight about ordering, I find, because we can't assume that all of the group members are going to see all of the messages in the same order. But we can assume that the messages sent by one particular group member, those messages will be seen by all the recipients in the same order. So we have this order per sender, essentially. I think of it as these like vertical stacks, and where across the different users' stacks, like you might have things happening in any order. But if you look at just one particular user at a time, we can just number the messages that they send sequentially and ensure that everybody will apply those messages in the same order. I guess this is assuming that the users are well behaved, isn't it? Because like a malicious user could send messages that would confuse the system.
Yeah, I guess one way to think of it is like each user is in charge of their own sender key. So it's like here, update the key in this order because I told you to.
Yes, and then we get the cheaper cost of updates, because when you acknowledge that you received somebody else's key, that is just an unencrypted message that can be sent to everyone. You don't have to send that individually via the pairwise channels to every other user. That can just be some kind of unencrypted broadcast. Yeah, so there seems to be one subtle point here, which is that we're kind of assuming that there is some sort of broadcast channel that exists. So if the only way you can communicate is pairwise from one user to another user, then have we really gained very much? Because, it might seem like we might as well just use pairwise signal channels in that case, because if we have to do this pairwise communication anyway. Maybe Daniel, do you have some commentary on that?
Yeah. I mean, with a all decentralized system, you can always also fall back just on the server to help us with the broadcast. It's then just an optional thing you can do, and it still works if you have your partition and you're on the plane with a coworker and want to continue working. Other than that, for instance, gossip networks, where I decide for every message that I receive, I send it to 3 other people and everyone does the same. Those are known to work quite efficiently in terms of the total number of messages sent to the system. So they are one approach, how we can use our ability to use broadcast to make the system efficient. But there are also inherent like broadcast systems. So if you, for instance, consider, I think 5G has some modes where you can broadcast within a cell. You can have Bluetooth broadcast, and it just offers new ways to do this, and it also offers the way to do things through other network topologies. So if we, for instance, then replace our standard internet with something that understands broadcast, then that's pretty cool and makes things efficient. Or if we might talk about anonymity networks, and some of them have a very intrinsic broadcast mechanism. So in these cases, it becomes very favorable to be able to make use of that, because that reduces the costs of your protocol a lot.
Yeah, and your point about anonymity networks is interesting. This is maybe something we can come to in a future discussion, but you've been doing a lot of work on broadcast in anonymity networks, haven't you, Daniel?
Yeah, and happy to have some future version of this on this topic, but probably would go like down the rabbit hole now, so I'm trying to avoid.
Yeah, so I think your point about gossip protocols is really important, because that means like even without assuming any changes to internet infrastructure, and like IP multicast basically exists within single data centers, but not really across the public internet. So we can't realistically rely on IP multicast, but we can use a gossip protocol where one user sends a message to 3 others, and each of those sends the message to 3 others again. And so within a small number of hops, you've just flooded the message to everybody. And that essentially gives you broadcast at fairly small cost, because each individual user only had to send 3 messages. So that's pretty cool. At this point, do we have any questions from anyone in the audience? Anyone like to interject something? If not, we'll just keep going. But just want to encourage people to put up their hands as well, if you like.
Or just type it in the chat if your microphone is not working or something.
Can you guys hear me?
Yes. Hello.
Yes.
Is that Alex?
Hi. It is. How you doing? Hang on. I can also do this. Right. I had one question which was more related to the forward secrecy, like post-key compromise stuff, and it might be a little off topic, so
Go for it.
ignore it. But it is related to post-compromise security in CRDTs where you depend upon changes that someone has made after their key was compromised. Because I'm trying to imagine how you handle that. So say I'm working on some data that depends on some data that was on someone else who's then depending on a compromised material. And I know that was a compromised change, but they didn't. So they incorporated it into their document. And then I have to decide whether or not to accept that change. I don't know if there are any frameworks for dealing with that situation.
Yeah, that's a really interesting point. Matthew, do you want to say anything about like the assumptions we're making about the scope of compromise and what an adversary will do or can or cannot do?
Yeah, so I guess there's two ways to think about compromise. So actually the usual way that people talk about it, just because it's the easier way, is to say that compromises are passive. So like an adversary will get your keys and they're just using that to eavesdrop. They're not using that to try to actively interfere with you. Yeah, there's some work that tries to think about what happens if an adversary starts impersonating users with these compromised keys. We just kind of brush it aside for now because it's harder. Yeah, I guess in terms of the CRD, like what you're asking about, you probably have to handle that at like the application level in the CRDT somewhere, like have a way to undo or whatever. I mean, I guess probably the same as for like any form of vandalism in like a Google Doc, just like undo it until it's gone.
I guess the complicated thing with the CRDT is that by the time it gets to you, you don't necessarily. I guess you just have to reject all of the changes that depend upon a compromised change.
I guess so, yes. So I guess one... Oh, sorry, Alice, do you want to say something?
I think the other thing to note is that you might never know you were compromised. So it may well be that if your device is hacked and then you get a software update and that kicks the malicious actor out, the user may never know that they were compromised. So it's sort of hard to know quite what to do in that setting, I suppose. And as Matthew says, I think it's of course much more likely to get a copy of the document, and perhaps depending on the setting, maybe less likely that they actually try and actively modify the document. So there's those kind of factors to bring into play as well.
And there's with post-compromise security, it's a really slightly fuzzy thing, because if you make no limitations on what the adversary is allowed to do, then there's nothing you can achieve, really. Like if the adversary is allowed to compromise somebody and then arbitrarily replace network packets with other packets, perform person-in-the-middle attacks or things like that, then there's nothing you can do. On the other hand, you can take the other extreme, which is the entirely passive adversary assumption with no network interference. And then there's like middle ground, and that's kind of really fiddly to define. So like, I think we make an informal argument in our paper that our protocol is secure as long as a key update happens before the adversary starts using the key material actively. So that is where we assume that it is possible for the adversary to interfere with the traffic, but maybe not immediately. And so if we're replacing keys every day, then maybe like you have a 24-hour period of vulnerability. And if you manage to make it through that to the next key update, then we're back in safe land. But yes, it's kind of a bit weird to reason about these things. Another thing, I guess, that is relevant in this context is, so with the new auto-merge data format for CRDTs, as you know, we've been working with hash chaining. And so then that, in a way, limits a bit what somebody could do on the CRDT level with a compromised key, because at least they won't be able to forge vector clocks, which would have been the case previously, where they could send different changes under the same vector clock and then confuse the other users. Whereas at least with the hashes, they're not going to be able to forge a hash in any way since they get recomputed. And so then at least you do know that no matter what the hash graph is of these changes, if two users have the same heads of this graph, then the entire graph will be identical. It may, of course, contain changes that shouldn't be there, but then you can use the usual mechanisms for getting back into a consistent state. But at least you know that the users will have the same data on their screens, basically.
That was useful. Thank you.
Yeah. Does anyone else have any interjections or questions or anything? Otherwise, I guess we could talk a bit about the status of our protocol. Like, we have a sort of prototype implementation, but maybe Daniel, do you want to comment a bit on what that's looking like?
Yeah, sure. So, I mean, the prototype implementation mostly fulfills the purpose to make sure we didn't forget anything and it can actually work if implemented. In no way it's meant to be something that can be used in real world. The one point of the paper where we use it for is to get an upper bound on how much resources this takes CPU-wise. It's like a very non-optimized version. So if we know this runs fine, if someone puts in some time, it will only run better. And the other thing is to plot out how much traffic we would be actually using. And that takes into account that we have some form of broadcast channel available to us. And I think it's in that way similar to like the prototype implementation that you would find in related papers that are in this area. And then it's usually on companies like Signal or whatever other messaging app company you have that they go and say, hey, we want to bring this to a version that's ready for production. And then that will take a lot of effort because you then finally nail down, okay, which algorithm performs better here? What are the actual timeouts? What happens in all the difficult edge cases where someone drops his phone, gets a new one? And yeah, those things are like all of the tricky edge cases that probably take a bit more work to get right.
Yeah, and of course there's like the whole huge can of worms of key discovery and trust establishment. Like, how do you know that you actually have the right public key for another user? That's a question that we've explicitly left out of scope for this paper. We just assume that either you have a trusted server to give you the public keys, or you have some kind of other way of establishing trust, maybe via like a shared password, and that gets sent by some other established secure messaging channel. There are various things you could do there. So another thing that people often look like when they're looking at the efficiency of this protocol is they're saying, well, the MLS protocol that only has logarithmic costs in the number of group members, whereas your protocol has linear costs. Isn't that a lot worse? Like, is this cost really acceptable? So maybe Alistair, there's something for you to comment on how we've been thinking about like large groups and the cost of the protocol and such like.
So my philosophy is that if you've got a group of 10,000 people, it's not really secure anymore, nor is it really ever private. So there are really, I think, kind of human level limits as to what is worth paying the cost of end-to-end encryption for. And so I'm not quite sure where to draw the line, but certainly at the level of hundreds of people seems to me approaching the limit of what you might consider to be a reasonable group size where people might keep things secret. And so
I wonder, maybe you could make an argument from the Dunbar number. Just, how can you really trust more people than you can have a relationship with? Ergo, as an informal bound, we propose, on the order of the number of social relationships you can have as being on the order of the number of people you need to worry about trust with. Now we're just going to move on.
That seems like a good heuristic, yeah.
So there's definitely one. I guess the interesting thing is about would be in the corporate structures, whether they can exceed 150 or not. So if you were to take, I don't know, a national security agency, for example, do they think there are bits of information or documents that they care about that they might want to share with more than 150, but they would still, perhaps through training or a sense of community, would still protect or not. Yes, I like that as an idea, but certainly for the kinds of apps that I often tend to think about, which are those that support the private citizen collaborating with their friends or colleagues.
Yeah, I guess we've been thinking mostly about individuals rather than corporations, but actually if somebody knows the corporate setting and knows what would fit there, that might be something interesting to look at in the future.
I guess in the corporate setting, there's already things like Matrix out there, right, which use like a centralized, well, federated model, but they seem to be working with governmental size organizations fairly effectively on that kind of end-to-end encrypted.
And do you know if they're actually using the encryption for that, or are they just relying on private deployments of Matrix where, like, you assume a trusted server?
I'm not certain. I know that they developed a lot of the impetus for developing the encryption side of stuff is from sort of three-letter agency type stuff, but whether or not they're actually using it or anything, who knows?
Yeah, I mean, the work that the Matrix team are doing is really interesting, and we've looked at it a bit, and they have their own crypto protocol called Megolm, I think. Is that right, Matthew? Matthew's been looking at it a bit. Do you want to comment on it a little bit?
Yeah. Yes, Megolm. I think of it sort of like sender keys, where like each person has their own sending key that they use to encrypt messages symmetrically, and then people update their keys sort of in a rolling fashion. Like maybe every day or every 100 messages, you'll update your own sending key without an explicit instruction to everyone else to say, like, please update your sending keys too. So like over time, you get post-compromise security in the same way.
Yeah, so we've covered, like, the versus MLS comparison of logarithmic, and like decided that the linear cost is basically fine for the types of group sizes that we think are realistic, that have a realistic threat model. We've been talking to Matrix actually also on getting some example messaging traces to understand the communication patterns in like real life messaging scenarios, to see, like, over what time periods do what messages get sent, how long are those messages, who are the senders of those messages, when do members get added to groups and removed from groups, and so on. So we've only just recently got that data, and we'll be looking at analyzing that and seeing if we can extract some interesting insights from that. And that would then lead us also to a benchmark for these types of messaging apps, where, like, hopefully we can then have a sort of a realistic model of how messaging users behave as a way of then actually comparing the performance of these different protocols.
I think related to this, of course, is when you're using these for messaging apps, the number of updates sent and so on is going to be very different from if it was used as a communication medium to support collaborative document writing, for example. And so there's some interesting analysis in that direction as well.
Yes, and that's hopefully then our other work on CRDTs and collaborative apps will help lead to a better understanding of that as well, how the access patterns differ. Makes sense, because, like, if you're doing a Google Docs style thing where every single keystroke you type is a message, that'll have very different behavior from something where an entire sentence that you type is one message.
One interesting anecdotal point from Google Docs, actually, this conversation reminded me of, is Google Docs doesn't work with large numbers of collaborators either. Mm-hmm. If you've ever sort of been given a link to a Google Doc that's really busy, 10,000 people or something that's posted on the front page of somewhere, you get basically a static HTML version of it that's updated at regular intervals. Yeah. You don't have access to the underlying OT algorithm, which is not, surprising, of course, but it sort of shows that, in addition to, like, a reasonable argument is the existing centralized infrastructure also has these problems, and, there seemed to be intuitive understanding that that's okay and this trade-off is acceptable. This is a breakpoint.
Yeah, that's happened to me as well. And, like, I guess at some point it makes the transition from, like, a read-write document to essentially a read-only document. And they've just built that into the system. So that makes sense. So yeah, maybe we can comment a little bit on future work that we're planning in this area, because I guess nothing is perfect. It's not really 100% finished yet, like the improvements we could make to the privacy and security of our protocol. Maybe, Matthew, do you want to comment on that a bit?
Sure. Let's see. Yeah, so I'm trying to think. There's a couple of things that we'd like to adjust in the future. So one thing is hiding metadata. So currently, to make it simple, when there's things like people are added and removed from the group, we just broadcast those and say like, hey, this person is being added and removed. That's just so that you don't have problems where like two people are added concurrently and they can't hear about each other's additions because they didn't have the right keys yet. So that's something we'd like to be able to just put the metadata inside encrypted messages like everything else, so it's not exposed publicly. What are some other things?
Yeah, I think there's also a denial of service problem potentially, isn't there, if users are misbehaving?
Yeah. So basically, when you're sending out the secret and you're saying like, hey, here's a new secret, please incorporate it into your keys, you can do a tricky thing where you send different secrets to different people, and then they're going to get confused about the group state. And this could be in particular a problem if someone does this like right before they leave the group, or if it's like an adversary who's infiltrated the group and they're doing this just to mess with it. That seems like a pretty tricky problem to solve without destroying performance, though. It would be nice to have. I will say MLS suffers from the same thing, kind of to an even bigger degree, just because of the centralized model. As soon as you have a bad message, it's going to mess up everything.
Right, I guess with us, at least, once you have a bad message, it messes up only the sender of that message. No, it'll mess up everyone who's acknowledged that message as well.
Yeah, it'll mess up everyone. If you use sender keys, it'll only mess up the sender.
Right. Yeah, so hopefully those are issues we can still fix in the future, but it seems like we've built a pretty nice foundation here already, and it'll be interesting to see how this can be integrated with real apps. Maybe we can turn it into a production quality implementation at some point from our current prototype. But it's exciting to be able to actually support these strong security properties in a group setting without assuming anything about central servers or such like.
It might be nice also just to reflect on like the time period of which this work was done and how much effort has gone into it to get it this far. So, Matthew, when did you start working on this?
Let's see, the beginning of I started working on like decentralized messaging in general, beginning of my MPhil, which would have been September 2018, I guess. I think this project has been in the works since maybe like May 2019 or so.
So yeah, definitely a solid 2 years, probably more like 3 years once you include all the time that you spent like actually getting familiar with the whole topic. Because you originally designed a variant to the TreeChem protocol used by MLS, didn't you?
Yeah. So originally we were looking at like what's the easiest way to add concurrency to MLS. And then, so that was what was in my MPhil thesis. And then we kind of realized like, oh, well, there's no way this can get forward secrecy, because basically the way you handle concurrency is just by remembering keys forever. And then if you have to go back and reorder stuff, you can do that. So we tried to think of like, what's the simplest protocol that gets forward secrecy and is still decentralized? And then that's sort of what led to this protocol. And
that simplest protocol is still an entire A4 sheet of paper in very small font. Well, I guess these problems are not easy, but yeah. But Matthew has written a pretty solid security proof of this protocol, so we do have reasonable confidence that it is actually correct and provides the guarantees that we think it's supposed to provide.
So another area that I guess that we're looking at that we haven't talked about so far today is, oh, someone's got their hand up, George.
No worries. Feel free to finish what you started, and I can.
No, I was just going to shift topic a little bit. So go on.
I'm not quite sure if it refers more to the future of this protocol or to something that I'm not correctly understanding. I was interested in how you're dealing with flaky clients or mobile clients that come and go very often in the network. If you missed some of the gossip messages, assuming that everything is gossip-based, when you log back into the network, you might have lost a lot of messages. First of all, is there a way to get back what has happened in terms of gossip? And if so, is there a way to reduce the effects that this has in a passive adversary?
Yeah, that's a very good one. So in terms of like recovering from being offline, that's definitely something that happens a lot with mobile devices. They're offline all the time. Our protocol, as we wrote it down, just assumes that there's some kind of reliable communication channel. But we can handle this at the level below our protocol in terms of a mechanism for if two nodes connect to each other, they want to find out from each other what has happened since I was last online. Can you send me everything that I don't have? Which is actually very closely related to a protocol that I worked on with Peter over the last month. Do you want to say a few words about that, Peter?
Yeah, sure. As fun as it's been to use a Bloom filter. So, I mean, Martin wrote the first version, which is basically you have two hash graphs and you want to synchronize them. This is for auto merge, but of course, you know, Git commit histories have the same property. The naive solution is you simply send all the hashes you have and then delete all the hashes you don't need and then reply and say, yes, please send me those ones. This, of course, is very expensive, especially for auto merge where every keystroke generates a new hash. So we've spent quite a bit of time trying to figure out how to communicate this efficiently back and forth. And the sort of mechanical trick is we use a Bloom filter to pack the data into a tight space. So it's sort of 10 bits for 99% accuracy per hash. So yeah, the hard part, of course, is then you get into all kinds of interesting questions about how do you avoid sending a million copies of everything everywhere. And we've been experimenting with trying to like rebroadcast Bloom filters. So if you get a Bloom filter from someone, then you can send that on to another participant and say, anything in my Bloom filter and also anything in this other Bloom filter, you can pretend I already have that. So just, look in both Bloom filters to see if I need data. Though I have been wondering a little bit, Martin, whether that's going to increase is there some product of probabilities there? That should be
It'd be fun to do that analysis, yes.
Yeah. But I think there's actually a lot more work to do on this. And I think it's pretty poorly understood. Basically, I mean, we're kind of like we need to start layering gossip protocols on top of this, which is going to get expensive, but then you have to start considering different network latency for different peers. You have some peers that are very slow. You might ask them for a whole bunch of data because they spoke to you first, but then now you need to realize that they're not going to. And of course, you could build all these complicated features into your protocol to handle all this, but it'd be nice to get something sort of adaptive where you get good behavior for free. And the sort of strategy there so far, at least that we're working towards, is that you should basically send small chunks, request and send small chunks of data. And that way, you continually kind of update your peers and say, okay, well, I've got this, I've got this. So rather than sort of committing to saying to the first person who says hello to you, we're best buds forever, send me everything, I'm going to come to you first for all of my needs. You sort of say, well, send me a little bit. And then hopefully, the more network bandwidth you have between a peer and the more often they send you good data, the more often you'll keep asking for more. And so you sort of naturally get lots of good data from them.
Yeah, so the insight there is that we can, conceptually what we're building is a broadcast protocol. But the way it actually works is by storing the messages on disk and by having this pairwise reconciliation between any pair of nodes. And because the messages are persistent, that means like a node can restart, reboot without any problems. It won't miss any messages through that. It can catch up and get any messages that it missed from any other peer that happens to have them. And then, yes, the this is a slightly different model from what a lot of gossip protocols assume, because they're usually built around this assumption of ephemeral messages that, you know, if you missed it, then it's gone. But I think this approach that we've taken for
TCP
auto-merge
of gossip protocols.
Yeah. I think that approach that we developed for auto-merge will apply very well for these encryption protocols as well, because what is needed is essentially the same kind of thing. In fact, we might end up with the similar kind of hash chaining thing in the encryption protocol as well, because, I don't know, maybe that's an approach for ensuring that everybody received consistent messages. So to prevent the impact of a malicious user from sending contradictory messages to different users, for example. I haven't thought
All
about
this stuff is nicely self-contained as well, and doesn't really have too much sort of like auto merge other stuff leaking into it. You know, as long as you have a bunch of you need basically chains. You need like a join semi-lattice of hashes, and then you can send it. So it's pretty amenable to, you know, Git could adopt this. Yeah, right. Crypto protocols could adopt this. Maybe in time it will sort of like migrate off and find its own life outside the nest. But there's still a bit of work to do.
Yeah, and I actually I want to do a bit of work on this. Heidi and I wrote this paper describing exactly this kind of hash chain reconciliation protocol. We haven't managed to get that accepted so far, because what the reviewers are always asking for is a performance comparison to other approaches. And so I want to really try it and compare to Git, for example, and see like how many round trips does Git actually need to reconcile these two histories? How many commits does it send redundantly that the other side actually already has, but it didn't realize that it already had? And so on. How many bytes do actually have to be sent over the network in order to get these two peers in sync?
We've got a little bit of a benchmark I've been putting together where I'm able to count the number of messages. We can probably do the number of sort of time steps it takes to synchronize for different numbers of peers and different kinds of overlay networks.
Yeah.
So that's handy. But I have to say, anecdotally, the Bloom filter generation is incredibly expensive and slow still, and we're only just now starting to poke at it. I'm not sure how fundamental it is versus incidental to, you know, it being new code, but it's definitely still pretty excruciatingly slow, and that's kind of an ongoing area of work.
The Bloom filter itself ought to be really straightforward, because it's just
it's
storing a couple of bits, but
it's keeping track of all the hash, like sent hashes. I found was taking like 10 seconds of the 20 seconds that, because you don't want to send the same hashes over and over again, so we just delete anything you've sent before. So it's just a bunch of stuff that's kind of naively implemented, but there's like this tendency with these things to, you know, you fix the problem in front of you, and that's how you end up covering an entire A4 sheet with, you know, 10-point, you know, font. And what I'm really trying to do as we're working is to say like, okay, well, can we remove something so that we don't have to fix this problem anymore? Can we change the way sync works? Like, I think incremental Bloom filters would be really nice. I've also been wondering if we could do fixed size Bloom filters so they're more reusable, but basically every, you know, we always send 1,000 hash holding Bloom filter, but we might end up sending 10 if you have a lot of delta between you. And that way, maybe we can find more ways to overlap them or reuse them or reduce recomputation or something. I don't know. It's very early in my thinking.
Potentially, yeah, definitely good stuff to explore.
I'm working on a... Sorry, Karen. I was going to say I'm working on a project that has a similar problem where we represent a lot of Git repos as a single Git repo and then sync the whole thing over Git. And that we're kind of writing some custom components that do a similar thing to the auto-merge sync protocol, but using XOR filters rather than Bloom filters.
Because, oh yeah, you sent that link.
Yeah, so the nice thing about those is you can calculate the intersection of them as a XOR, which is useful if you have like some nodes which are kind of a super node type thing where you don't want to keep recalculating Bloom filters every time you have to calculate the intersection with some other peers set of hashes. You can just do a quick XOR with a XOR filter, and that makes things easier if you're in a sort of not entirely peer-to-peer topology.
That's interesting, something to look at. And Doug also sent a link to a paper on using Bloom filters for peer-to-peer keyword search, which also looks very interesting. So thank you for that.
Yeah, I have this theory that I'm looking forward to exploring at some point in the distant future, which is that the idea of a DHT is like a good idea, but in this kind of work, it's being poorly applied. Like the DHT assumes you have no sort of social coherence to data, that any node on the entire internet has equal probability of holding the data that you want. And so, you sort of fan out over the IP space to try and find things. It's like a very succinct and detail eliding description of a DHT. But probably the data that you want is on the computer of the person that you're talking to already. It's a very high probability that if you're collaborating with someone and you need some changes for a file you're working on, that they have it. And if they don't have it, probably somebody that you both know have it, right? For regular collaborators.
Yeah.
And so there's some kind of like social graph influenced form of a DHT that I think could really help. And in particular with peer-to-peer sort of low trust routing, part of the reason why you have these like intervening nodes like the RIAA in the United States sending people cease and desist is they can just sneak into the DHT and monitor traffic and then like send cease and desist letters to people. So you can flip that around and say, well, no, you only actually talk to people who you've met before. You only ask people you've met before. Then it like closes down just the privacy scope quite a bit, but two, it also just reduces the amount of traffic and like flux and sync and so on. You might also be more likely to help people if you know them.
That's really interesting because like one of the things about like pastry as like a historical DHT that it added to everything else was that it had geographic proximity awareness in how it constructed the overlay network, so that it was more likely that you would send messages to nodes that are close to you in the underlay network. So that's interesting to maybe think about doing that proximity metric instead with a social measurement instead of a geographic measurement, so that you still have the nodes that you don't know socially as a fallback if you can't find the content close to you socially, but you would sort of prefer the ones that you do have already communication experience with if they have it.
Yes, I think that seems like a really promising direction.
I think there's also like the overlap there is sometimes reasonably high. The people that you socialize with also you meet geographically, not always, but there's definitely a correlation between those two. I guess in
less so these days.
It's a bit different, but so maybe you can also, from a security perspective, you get some additional assurance if you're meeting someone physically through the same Wi-Fi access point, because the attacker would then have to compromise all the places where you meet. And so one of the other projects we have looking at, which is we've not really talked about so much today, is how do you know that the person you're talking to, or you think you're talking to, is the real person, right? So one of the challenges you had in the end-to-end encrypted messaging space is when I get given a key from Facebook's key server, is this really Alistair's key, or is this someone else's key pretending to be Alistair? And how do we do the checking for that? So we've also been looking at gossiping protocols from that perspective. And these two things may actually be very much connected. And you could use the same kind of mechanisms for both.
Have you been following our work at Ink and Switch on, I don't know if Martin's told you about what we're doing with Backchannel.
I think no, please tell us.
Yeah, so Cade Deem of the New Design Congress is sort of a security designer. He's got, good credentials. He used to work on Spider Oak and all that. And now he's got this sort of independent group. And he basically posed a very provocative idea, which was that the whole reason phishing and spoofing and all these attacks work in the first place is because you have identity in the system. You don't need identity in the system. In fact, that's the weakest link. There are already lots of good ways to establish identity between computers or people outside of your system. And so if you remove this sort of like really weak layer of identity validation in the technical system, then you actually buy back a lot of capability because you sort of remove an attack vector. And so people are forced to then rely on better systems that they automatically sort of grade to the scenario. So a good example would be like if you and I were going to discuss something private, I might want to jump on a Zoom call with you rather than sending you an email because I wouldn't want to leave things written down. But there's no sort of equivalent of that in terms of identity verification for an email, right? Like we have a whole robust sort of socially determined system of sort of like risk management outside of these sort of identity systems. And historically, we've done a really terrible job of successfully securing them, right? It's easy for me to change my name to Mark Zuckerberg and then set my profile picture to his picture and start messaging people. You know, the blue check doesn't scale. And so what we're doing with Backchannel is basically trying to move to a model of pet names and monikers where you establish trust sort of independently, and then you exchange a PAKE key, which is a short-lived single-use sort of introductory token. And once you've exchanged that, you do that using, you know, any appropriate system. And we're currently working with sort of journalists and lawyers who work with sort of high-risk clients who, you know, might feel uncomfortable about using existing infrastructure. And so the idea is, for example, talking to a journalist, you often meet someone in a Starbucks, right? They want to see you. They don't want to give you files. They've never met you before. They show you something on their screen on their computer, and then, you know, you say, okay, great. Well, now you have to give this to me. And so you can exchange a PAKE key verbally, you know, 17, you know, monkey spaceship, and then they type that in, and then they can send you the data because you've used the in-person trust to bypass any risk of sort of intervening identity hijack. And so then once you have that channel, right, then you can use existing security protocols to then maintain that channel over time. And so you sort of leave the identity out of it. It's more like a phone book, you know, it's hard to spoof because when your phone rings, you know, you may not, you just get a phone number. If you don't recognize the number, you go, I don't know who this is. It's much harder to spoof. Of course, then the phone company identity. That was a later mistake and has led to all kinds of problems anyway. So maybe that's more evidence that this is the right way to do it.
Yeah, I think this seems like a really promising direction.
It's interesting also how things come around, because pet names, I think, was what, 2005 or something of that era.
Oh yeah.
P Labs. So sometimes these things kind of take a while to find the right use case. And I guess it's early days yet, but maybe if this does find the right use case, it's interesting. That's 15 years later.
Yeah, the RDT started in what? So 04, 08?
08-ish, I think, yes. Okay, well, we've gone about an hour, so I think we've covered a lot of ground. So I think maybe we should gradually wrap up unless anyone has any more things they want to talk about. Then thank you all for joining. I think this has been really fun and really interesting, really good exchange of ideas, and good to get some people together who hadn't met each other before, but hopefully it's been interesting for you. So thank you all. And I think we'll check that the recording is okay. And if it's all right, we'll probably put that online as well. So I hope you, unless anyone has any objections to publishing the recording. Okay, great. Then let's call that a day. Thank you very much for joining, and nice to see you all.
Bye-bye.